Welcome, everybody. Good morning, good afternoon, good evening, depending on from where you are attending. Welcome to the Hypatia Colloquia of today. This is an initiative of the Offices for Science at the European Southern Observatory, target to early career scientists. Today, the event is target and dedicated to two wonderful telescopes, one in existing one and the one which is in construction. So we have for the first speaker talking about the 30-meter telescope and the second one about the Subaru telescope. So I leave now the forum to the chairs of today. So we have a student at ESO, so Paul Lowe. So please, Paul, yes. And then we have a staff, ISM staff at ESO. She will chair the second talk. So yes, welcome Teresa, and thank you for helping us. So please go ahead.
Yep, thanks Paula for the introductions. So my name is Chien Paul Law. So I'm a ESO student in ESO, and I will be chairing the first sections. So give a first brief introductions to our first speaker, she is Ramya Anche. So she is currently now a postdoc researcher in the University of Arizona Stewart Observatory, and she did her PhD in the Indian Institute of Astrophysics. And the stage will be all yours, Ramya, to share about the polarimetry capability of the 30-meter telescope.
Thank you, Paul. Can I share my screen now?
Yes, please.
Can you see it?
Yes.
Okay, thank you.
Yep, the stage all yours.
Yep. Hi, everyone. I'm Ramya. I'm currently a postdoctoral research associate in Stewart Observatory. I finished my PhD in Indian Institute of Astrophysics, and this is one part of my thesis work where I estimated the polarimetric capabilities for the one of the next generation large telescope, which is 30-meter telescope. So this is a structure of the talk. I'll just give a brief introduction about what's polarization and what are the polarization science cases in astronomy, and what are the challenges in accurate optical polarimetry, and polarization model for the 30-meter telescope, and how did we estimate the polarization aberrations. With all these in mind, the conclusion is what could be the possible second generation polarimetric instruments for TMT. So what is polarization? Basically, polarization is nothing but the direction of oscillation of the electric field vector. As the electromagnetic wave propagates, if the electric field vector keeps vibrating only in one particular direction, it's called a linearly polarized light. If this electric field vector traces a circle as it propagates, then it is called a circularly polarized light. And also, most generally, the light is unpolarized, where it doesn't have a preferential direction of vibration, where you can see that it looks something like this. When it passes through a polarizer, it gets polarized either in the vertically polarized direction, or linearly or horizontally polarized, or circularly polarized. So basically the electric field vector direction is not the vibration of electric field vector is nothing but the polarization. Since we have to measure the direction of electric field vector and its amplitude, so but the only way we can measure the light is its intensity. The parameters we use for the measurement of polarization are called Stokes parameters, which are defined as IQ/UV. What it basically defines is I is the total intensity of the light, Q is the polarization along instrument X and Y axes. It's like you keep a polarizer in an X direction, you keep a polarizer in a Y direction, and measure the light intensity. And U is the polarization along instrument plus 45 and minus 45. That means you keep the polarizer in 45 and minus 45 and measure what is the intensity of the light. And V is the circular polarization. Since Q and U correspond to the linear polarization, the degree of linear polarization is obtained from Q and U, and degree of circular polarization is obtained from V and is from V. The another formalism we use in polarimetry is called Muller matrix, which is a 4x4 matrix which defines the linear relationship between the input Stokes vectors and the output Stokes vectors. So what happens is, if you give a particular light of particular polarization into the system, and the system changes or modifies this polarization, the properties of the system could be represented in 4x4 Muller matrix, which can actually change the input polarized light. Another representation of this is how it changes one Stokes parameters to the other Stokes parameter. So for example, the first column in this, whatever is shown in yellow, it's called as instrumental polarization, where you don't have any polarization from the source in the input light, but the system introduces the polarization. And the ones shown in red are called crosstalk, where the system is converting one polarization state to the other. And the one which is in green is called a polarization rotation. That means it is rotating Q to U. It is just changing the direction of its direction of the electric field vibration. So where do we see polarization in astronomy? I'm just giving two of the science cases. One is the most common science case, where you have the polarization of the dust. So since most of the stars are spherically symmetric, they are unpolarized. So once we get the unpolarized radiation coming from the star, and on the way there is interstellar dust, and these dust grains arrange themselves up in a particular direction and in the presence of magnetic field. When that happens, the unpolarized light passing through this dust grains either gets polarized in one particular direction, either because of the scattering or because of the dichroic absorption. So what we see here would be a polarized light. And in another case, in the case of exoplanets and debris disk measurements, the light from the unpolarized stars goes to the disk, and because of the dust grains present or the molecules in the atmosphere of the planet, it gets polarized, and what we see is the polarized light. So we get to know a lot of information about the dust grains or the molecules in the atmosphere because of the polarization. So what exactly is a polarimeter? Polarimeter is nothing. It can be an add-on component to any of the spectroscopy instrument or an imaging instrument. What it consists of is a Wollaston prism and a halfway plate. Wollaston prism is the one which divides the incoming light into two orthogonal components. As I explained, I said we have to measure the intensity on the X direction and the Y direction in order to measure Q. So Wollaston prism splits the light into I0 and I90 components. And in order to get I45, I135, instead of rotating the Wollaston prism, we rotate the halfway plate, which is easier to rotate. So we get I45 and I135. So this is how we measure the Stokes parameters Q and U. But how does it look on a CCD when you look at when you get a polarimetric image? It looks like this. For every star, we get two images where we measure the intensity in this image, which corresponds to I0. We measure I90, which is another image, and then calculate Q and U. So this is how the polarimetry is done in astronomy. What exactly are the challenges for accurate polarimetry? One, it is also limited by photon noise. Second, because you have to take two measurements, it is also limited by atmospheric scene and variable sky background on your image. If the sky background is not estimated properly, then it can result in errors in the polarization measurement. The other important aspect is the polarization introduced by the telescope and the instrument optics. What happens is, because every reflection from an optical surface or a transmission is capable of changing or introducing the polarization to the incoming light, it actually affects in our accurate polarimetry and also in the case of high contrast imaging. For here, I'm showing an example where you have a linearly polarized light getting reflected off a mirror. So what happens is, because of the reflection coefficients introduced by the mirrors, because of the reflection coefficients, and which is mainly a function of the coating which is present on the mirror and the angle of incidence, the mirror is capable of modifying the polarization of the input light, linearly polarized light, into an elliptically polarized light. So when it gets reflected off a surface, you get an elliptically polarized light, which is not the one which is input on the mirror surface. So it's very important to estimate the actual polarization which is introduced by the optics before we actually design a polarimeter for the telescope. So what are the different effects from the telescope? As I had already explained, the first one is the instrumental polarization, where the star is an unpolarized light, what you're getting, but whereas the telescope is introducing the polarization to this. So we measure all the 4 Stokes parameters, which is called instrumental polarization. Crosstalk is when the star is giving a linearly polarized light, but instead of measuring linearly polarized light, you measure circularly polarized light. That means we measure elliptically polarized light, that is some amount of linear to circular conversion. And depolarization is loss of polarization. How is this corrected in the present polarimeters? So in the case of unpolarized light, what we do is we observe an unpolarized standard star for a very which are known to be unpolarized for a very long period of time, and we correct in our measurements. That means this is introduced from the telescope and we just remove it from the data. But in the case of linearly polarized light, we also observe polarized standard stars which have same polarization for a long period of time. We use it to correct for the rotation as well as the position angle correction. But whereas in the case of telescopes which are going to be next generation, which are large telescopes, it is better to know in prior to how much the polarization is introduced by the telescope, so that we can plan these kind of observations. So with this motivation, we started to model the polarization for the TMT telescope, and also to estimate how does it affect our polarimetric and non-polarimetric science cases. So 30-meter telescope is a next generation large telescope with 30-meter primary mirror diameter, which is going to be built in Mauna Kea, Hawaii. The wavelength of operation is 0.32 to 28 microns. The primary mirror consists of 492 hexagonal segments, and one of the segments is shown here. And it's a Ritchie-Chrétien telescope. It has a fold mirror in its optical configuration. This fold mirror rotates in order to feed light to different instruments on the Nasmyth platform. Before we started modeling for the 30-meter telescope, we collected about 40 polarimetric science cases, 2 of which the examples are given below. Each of the science case gave what is the level of polarization observed in that particular science case and what is the acceptable instrumental polarization. And also they gave wavelength of operation and the field required to observe, etc. So we had all the requirements before we started modeling. So the model is this is the brief idea of the model. It is called the polarization ray tracing algorithm, where we determine the changes in the polarization at every optical surface in the telescope. So first we define each optical surface of the telescope and we launch rays with a specified polarization. Then we trace the rays through all the mirror surfaces. At each surface, we estimate what is the Fresnel reflection coefficient, how much of reflection you're getting from the surface. And we also determine the direction in which these vectors are, like how the ray is changing as it propagates through the optical system. And since we have input the electric field vector of a specified polarization, we find out how this electric field vector changes after each reflection. Then we finally estimate Stokes parameters and degree of polarization. In this analysis, our primary mirror was monolith, and also the important thing in the polarization ray tracing algorithm is when we go from one surface to other surface and trace the rays, we have to keep all the coordinate transformation with respect to one fixed plane. It has to be taken into account. So all these things are taken into account and we perform the polarization ray tracing. What we use, the important concept which we use in our algorithm is the coating of the mirror, which is Gemini coating, which is a 4-layer coating consisting of silicon nitride of 85 angstrom, which is the protective layer, and silver is the main reflective layer. And we do not consider the inhomogeneity or the dust deposition on the mirror surfaces. We get Stokes parameters and degree of polarization from the model, and we also get the Muller matrices of all the mirrors. This is one of the plot which we simulated for if you have the incident angle variation on a flat mirror surface for different wavelength, and for the Gemini coating, how does the polarization look? This is the instrumental polarization. You can see it's as high as 5% in the blue region, and this is the crosstalk, that is how much of linear is getting converted to circular, which is as high. It goes about 100%, even in 60, where it starts acting like the mirror starts acting like a retarder. So this is the first simulation we did. And this actually gives the Muller matrix of the primary mirror of the TMT, the 4x4 matrix, which I was talking about, which this basically shows this is the instrumental polarization, and this is the crosstalk, and this is the rotation. For the primary mirror is a rotationally symmetric mirror. So because of which the identity, whatever the Muller matrix we get is an identity matrix. But whereas we do see the contributions from different parts of the mirror here, but what happens is when you go to the primary mirror focus and you average these components, since one quarter of the mirror gives a positive contribution and other quarter gives a negative contribution, this gets cancelled. So all the elements gets cancelled except for the diagonal elements, which is, so it's going to be an identity matrix. So the primary mirror, which is a rotationally symmetric mirror, does not introduce any kind of polarization. So this is at the azimuth focus of the TMT, that is after the fold mirror. So this is how the instrumental polarization and the crosstalk vary. So we can see that the instrumental polarization is as high as 4.5% in the blue region, and it reduces to 0.6% in the redder region, and it also varies with respect to the field angle. We see the same behavior as well as in the case of crosstalk. And this happens, the field angle variation is mainly because it is asymmetry, because you're not when the field changes, it is an asymmetry behavior which is introduced in the system, and in the behavior with respect to the wavelength is mainly because of the change in the refractive index. Later, we want these two. This is an azimuth platform of the 30-meter telescope where we have different instruments placed. In this, these two are the first light instruments, and they do not have the polarimetric capability. So it will be one of the second generation instruments which might have the polarimetric capability. So we wanted to see how the Muller matrices or the polarization effects changes from one instrument port to the other. In the case of TMT, what happens is it is an ALTA system. So the primary and secondary mirror moves tracking the star in the sky. But whereas a tertiary mirror does not move with the telescope, it readjusts its tilt as well as the rotation in order to keep the light constant on the instrument. So when the telescope is tracking, that is when the zenith angle is varying, the tilt as well as the rotation of the mirror are varying. So we wanted to see effect of this on the polarimetric measurements. So this is a Muller matrix for different instrument ports. Here I am showing it for 3 instrument ports on the plus X azimuth platform of the telescope. What we see here is when you rotate the mirror from its reference position to another instrument port, we have to include a rotation matrix. We have to include a rotation matrix in our analysis in order to rotate the coordinate system. So that is what is the one which has to include if we have to if any of these instruments have polarimetric capability, the only change in the model would be including this rotation matrix. Then what happens when it changes with the zenith angle? As the zenith angle changes, because the tertiary mirror is tilting and rotating continuously when the zenith angle is varying, we have the instrumental polarization as well as the crosstalk keeps varying when the zenith angle varies, which is a kind of a problem because because you need to have the standard star measurement at every zenith angle in order to correct for it. So this is shown for 2 of the instrumental ports, that is Nefarious and Heteros, where you can see the variation of about like 2 or 3% in the crosstalk and also about 0.1% in the case of instrumental polarization. So what are the results from this analysis? We found the fold mirrors are the main source of polarization, and instrumental polarization, crosstalk, depolarization vary with field angle, zenith angle, and wavelength. To obtain the linear polarization observation, we have to measure the circular polarization. What are the solutions? One, we have to avoid the fold mirror. That means you can do the modulation or you put the halfway plate retarder before the fold mirror, which is not possible in TMT because of its beam width. Or you can try the mitigation of polarization, adding another crossed fold mirror such that it cancels the effects of this fold mirror, and accurate polarimetric model for offline corrections. So the first one we tried, that is using another cross mirror configuration in order to cancel the effects introduced by this fold mirror. What happened is whatever the polarization introduced by this mirror, it gets cancelled by another mirror which is placed in an orthogonal position. This was previously implemented in sphere instrument of VLT. In ours, when we tried this analysis, we could actually get the polarization cancellation up to 0.1% from 4%, and linear to circular crosstalk reduced to 4% from 70% in the blue region. But the only problem is when the tilt of this mirror keeps changing as the zenith angle changes, we have to vary the tilt of this mirror as well in order to keep this cancellation constant. Otherwise, there is a leakage term which gets introduced because of because these two are not aligned perfectly. Then we went to model it to include a more accurate model, because we hadn't included the segments in the primary analysis. So as I mentioned, the primary mirror consists of 492 segments in 6 identical sectors, and each sector has 82 unique segments. And each segment is about 1.44 meter size across the mirror, and there is a 2.5 mm gap in between the segments. So this analysis we performed in the optical design software called ZMAX. So we simulate this mirror in the ZMAX, and this is a polarization pupil map which we obtained from ZMAX, which shows that if you input a linearly polarized light, after the tertiary mirror we get a elliptically polarized light, which we were seeing since from before. So what are the different effects we analyzed? Since it is going to, since the primary mirror is going to have 492 segments, all the segments will not be coated at the same time. So at any time, there will be a segment which is freshly coated, and there will be also a segment which is coated like 2 years ago. So there is a variation of refractive indices from segment to segment. So in order to incorporate those changes, we varied the refractive index of silver and silicon nitride from segment to segment. We generated this distribution of refractive indices and gave different refractive index to each segment in order to see the spread in the instrumental polarization. This mainly was to give an idea that whatever the values we estimated before, this gives a error bar on that. That means if the segment to segment variation is there, this is the error which we can expect on the instrumental polarization and crosstalk measurement. We also try to see if the recoating sequence of the segment, whether it has to be done ring-wise or the sector-wise, and also tilt and piston variation of the segment, how does that affect the polarization capability? So the last thing which we checked was how does this instrumental polarization affect the non-polarimetric observation. So this is one of the simulations done where you have an exit pupil with no polarization changes, and there is no error, there is no wavefront error in the system. Then we get an image plane PSF which is perfectly circular. But if we had two polarization variation in the exit pupil of the system which is completely orthogonal, like two extreme polarizations, then we get a PSF which is incoherent, that is stretched in one particular direction. This asymmetry is seen mainly because of the polarization introduced by the system. So this is estimated using a formalism called as Jones pupil map. So what we do in this is we give an expolarized light at the input of the telescope. That is, we are just giving a horizontally polarized light where you have x, the amplitude of electric field vector is 1 in x, it is AXX is 1, whereas EY is equal to 0. So if it is an ideal system, as the rays propagates, then in the exit pupil we should see only this component and AXY should be 0. That means ideally system should not convert any x polarized light to Y, but we do not see that. We see that some amount of x gets converted to XY, which is a cross component. Similarly, we see the behavior for Y polarized light. And also what we notice is this the effect what the system does for X polarized light is not same as Y polarized light. So we have the difference between these two. Along with that, it introduces different phase components for X and Y polarized light, which is the main reason in the case of polarization aberrations. So when we take a Fourier transform of that, the electric field vectors in the exit pupil, what we get is a PSF for the X component. Along with that, we get another component which is called as ghost component. And this is what causes an asymmetry in the final PSF. So our total intensity Ix will be addition of these two, because of which we see a small asymmetry in the one direction of the PSF. In the same thing for the Y component. So in an ideal system, we get your cross components will be 0 and you get only this PSF. And if you are looking at an unpolarized star, it will be only unpolarized. But now because of this, you cannot actually because there is a cross component from X and Y polarization, this will introduce the asymmetry in this unpolarized star PSF, and because of which there will be a problem in the high contrast imaging measurement. And we also estimated if there is an aberrations which is introduced, that is we have coating induced astigmatism, we have tilt, as well as chromatic aberration, which is all coating induced, and polarization aberrations. These are not the aberrations which are actually present in the system, but these are introduced mainly because of the coating. And because of which this is called the ghost PSF. It varies from 10 power minus 4 to 10 power minus 6 in the optical and near IR wavelength. With all these estimations, in the conclusion, the two possible second generation polarimetric instruments for TMT would be, one is MICHI, that is mid-infrared polarimetric instrument. As we see that the polarization effects are much lower in the mid-infrared region, it makes sense to have a polarimeter in the mid-infrared region. The other one is a planet system imager, which is expected to achieve a high contrast. So all the all the estimations we have done about polarization aberration will be useful for PSI. So what are the takeaways from the talk? Our instrumental polarization varies from 4 to 0.6% in TMT in the wavelength range of 0.35 to 2 microns. And instrumental polarization, crosstalk, depolarization, everything vary with the field angle, zenith angle, and wavelength. And polarization effects reduces for mid-IR wavelength region. So we can do polarimetry in mid-IR, and polarization aberrations give rise to ghost PSF, as we have seen. And this effect we are going to, the effect of ghost PSF will be simulated like in order to see how it affects the achievable contrast for the PSI. And these were my thesis supervisors, and these were my collaborators. And yeah, thank you.
Thank you very much, Ramya, for the very nice talk about the polarimetric polarization capability of the 30-meter telescope. And I would want to open the floor. Sorry for my camera. I would want to open the floor to any questions from the Zoom and maybe from the YouTube. Well, maybe while others are actually thinking about questions or things, I have a very naive questions. So one thing is you mentioned about when other than mirror, and I think there's another important thing is about the halfway plates, right?
Yeah.
So when you have in here you have talked about instrumentation polarization mainly from the mirror, and have you also taken account what would happen if there's extra impact from the halfway plate, and will you have to take care about or in the near future, or that's actually could be something is much more negligible compared to the mirror?
Yes, actually for the MICHI, as I was mentioning, which is going to have the polarimeter, for that we have simulated the entire polarimetric system, because we have the initial design for it. So we, because it has a halfway plate Wollaston prism system, so we did simulate its how much the instrumental polarization is after halfway plate and Wollaston prism. We have done that for MICHI.
But that is really comparable to the mirror, or like which is or comparable?
It is higher than the mirror because
wow.
It's the optical component, right? So that's why.
Yeah. Thanks. Yep. And I see Paula's hands and Teresa. I mean, Paula, you may go first.
Okay, thank you, Paul. I think for Teresa raised his hand before me. Anyway, thank you. I maybe very naive questions because I have no. I'm not a specialist of polarimetry. I was wondering whether, since you mentioned that in the mid-infrared or near-infrared, depending on the wavelength, you have less problems to determine the effects, the instrumental effects. I was wondering whether you have suitable calibrator for impolarization in this wavelength range.
We still haven't, because we are still deciding for the second generation instruments, so they are still in the white paper stage. So we have done the preliminary analysis, but we haven't thought about the calibration yet.
Okay, of course the thermal background is pretty high, so I was wondering whether it has any influences on the calibration. Okay, but thanks a lot.
Yep, I mean, Teresa, please go ahead.
Hi, thank you for your talk. Very interesting. I have a question about coating, because you mentioned that it has quite a strong effect on the studies of polarization in general. So what happens, because you have a freshly coated mirror and then it degrades with time? So does it have a big effect then on the polarization that we measure, and how can you take this into account?
For the segmented configuration, as I mentioned here, we varied the refractive indices of the silver and also the thickness of the silicon nitride, because it can have a dust deposition. So we varied it within a radiation range of plus or minus 10%, and we try to see how does it affect. But in the primary mirror segments, the variation is very negligible. It doesn't affect much. But if we put the same effect on the tertiary mirror, which is a fold mirror, it does introduce it actually increases the percentage by about maybe 0.3 or 0.4% because of the variation because that is the main component which is introducing. So the option what we were thinking is to get the small samples tested and coated with these mirror coatings, and then test it in the lab in order to see how they change over time.
Yeah, exactly. Yeah, that was my follow-up question, how well you can then this verify in the lab. So I see that it's planned. Nice. Thank you.
Thanks, Teresa. And just to ask again if there's any more questions from the Zoom and YouTube. And yep. And if there's not, then thanks again for Ramya for the really great talk. And I would also pass the chair to Teresa to introduce the second speaker. Well, thanks again, Ramya. Yep, Teresa, thanks.
Hi, everybody. So it is my great pleasure to introduce our second speaker for today. His name is Kevin Barjot. He did his master's in the Paris Observatory at the University of Paris. At first, he did the general engineering and fundamental physics, but in the second year of his master, he specialized in astronomical and space-based systems. And now he's a PhD student at the University of Paris, and he works at the Paris Observatory in the Asia department. I would like to highlight from his CV that he has quite extensive work experience, the recent one from the Subaru telescope at Hawaii. So Kevin, you can share your presentation. The title of Kevin's presentation is the first light of the first visible fibered interferometer upgrade at the Subaru telescope. And with this, Kevin, I leave the floor to you. Please go ahead.
Yes, thank you very much. You should see my presentation.
Yes.
Okay. Yeah, thank you very much for the presentation. I would like to thank also for the organizers to let me present my work here at the Hypatia Colloquium. So I will talk about my PhD project, which is about the first visible fibered interferometer upgrade at the Subaru telescope in Hawaii. Yeah, I'm supervised by Elsa Ubi and Sylvestre Lacour, and you have the name of all the collaborators here. So the scientific topic of my research is direct detection of exoplanets. So here I put two images of such direct detection, in which you can see in the center a star from which the light has been diminished by the coronagraphy technique in order to let appear the exoplanets around. So here on the left and on the right, you have an exoplanet. And yeah, the goal of direct detection is to get the light directly coming from the exoplanet to study its composition by spectrometry. And the two technical goals we want to achieve to do that is to get high contrast, which is the ratio between the brightness of the star and the brightness of the exoplanet, which can be between 10 to the -3 to 10 to the -10. And the second technical goal is to get to high resolution, which is the separation, the apparent separation between the exoplanet and the central star, which is in order of tens of milliards seconds. So here I present a plot of the planet-star contrast as a function of the apparent separation. So these are the two technical goals we want to achieve. And you can see the solar system planets at the bottom, and you can see some performance ranges, capabilities ranges of some instrument currently operating with some already imaged exoplanets here. And in pink, you have the range that we can obtain with coronagraphy technique on 10-meter class telescope. And the technique I'm working on is aperture masking on 10-meter class telescopes, which has a range of capabilities here in green. So we can study other exoplanetary systems than we can already do. So that's why it's interesting. Yes, to explain about what is aperture masking, I need to get into some basics. So here I represent the pupil of a telescope, which is basically the surface that will collect the light from the astrophysical target. So here basically it's the primary mirror. And the light, when it enters the telescope, it will be diffracted by the telescope. And to understand this diffraction, we could take all the pair of points here in the pupil that are separated by the same length B1, for instance. And what will be ongoing is that the wavefront will interfere, like in a Young slit experiment, between these 2 points. And all the pair of points separated by B1 will contribute to one of these gray plot here on the right that we call interference pattern. So what you have to understand is that you have an infinite contribution to just one interference pattern here. And if we take another length B2 between two pair of points, you have another interference pattern with another spatial frequency, and so on with with all the separation you can take. And when you add up all these gray interference pattern, you get the red one, which is the well-known in the field diffraction pattern, the airy disk that you can see at the bottom here on the right. So in the perfect case, that's what you would obtain at the focus point of the telescope. So perfect case means no turbulences. The turbulence is the perturbations we get from the atmosphere because we observe on the ground. So this turbulence will just add a little term in phase in those interference pattern. So here if I take again all the pairs of points separated by the same length, it will be associated with a phase phi I plus a little term coming from the turbulence, which won't be the same on all pairs because the turbulence is different over the whole pupil. So when you do the image through the telescope with this turbulence, you got a blurred diffraction pattern. As I said earlier, you have an infinite contribution for every of these interference pattern for the same spatial frequency. So you will have a blurring. So that's the main problem of the atmosphere. So here it comes the pupil masking technique. It originally consisted in putting a mask with holes in front of the pupil of the telescope, or at least in the past, in the optical path of the telescope, with a separation between each of these holes that is unique, such that we select only one spatial frequency in the pupil plane, such that we have a unique contribution to to each of these interference pattern on the right here. So you avoid the blurring of the fringes of the image caused by the atmosphere. So the advantage of this technique is that we can recover the diffraction limit of the telescope, which is the resolution capabilities, which is in theory lambda over d, lambda being the wavelengths of observation and d the diameter of the telescope. And with this technique, we can even make twice better than that by going up to lambda over 2d. And the limitation is that we only use a fraction of the pupil, so we have less light and less throughput. So here I put a scheme of the instrument I'm working on, first instrument, which means a fiber imager for a single telescope. So from left to right, you have the pupil masking part here on the left. It's essentially a deformable mirror. Yeah, I put a picture of it here. So very small mirror with hexagonal segments that can be controlled in piston, so back and forth, and in angle, so tip and tilt. Then we have here, so as you can see on the picture, a micro lens array. So it's very little lenses of about 250 micrometers that focus that will sample the incoming light beam and focus light into optical fibers. And these optical fibers are monomode optical fibers. So the advantage is that they filter the wavefront from remaining aberrations that could remains after the adaptive optic system. So here the core of the fibers is 5 micrometer. After that we use optical delay lines, which is essentially just a mirror that can be controlled in position to change the path lengths of every of these optical fibers. It's needed for the interference part because we want to equalize the length traveled by all the optical paths. And here it's the integrated optic chip in which are recombined all the inputs. So I will explain that a bit more after that. I put here some pictures of these photonic chips. So on the left, you have a picture of the chip used in gravity in the very large telescope in Chile. And you can see some waveguides on the picture on the left. And on the right, you have the chip I worked on during my PhD. It's basically a block of glass in which have been engraved waveguides. It's like optical fibers. So you have some optical fibers on the left, which are the inputs. So there are 5. And at the output, you have more of them. I will explain that right after. And it's very small chip, so it's very practical to use it and to integrate on the bench. So here is a scheme of these waveguides inside the photonic chip. So you have 5. Here you have 5 inputs at the bottom, and then we want to split them in 4 to make interfere every input to all the other inputs. So it's pairwise recombination. And here you have the recombination part where you can see easily all the inputs that are recombined 2 by 2. And you have 10 outputs. And these outputs are sent into a spectrograph. First it was a prism, and now we are upgrading it to a new spectrograph with a better, a higher spectral resolution using a holographic prism. And at the end, you have here an image of what we can obtain on the camera. So you have in horizontal axis, you have the wavelength dispersion, and vertically you have each individual outputs of the photonic chip. And here you can see that there are some fringes, and you should see an animation of these fringes being modulated. So we move all the segments here on the left on the deformable mirror. We move them in piston, so back and forth, to change the path length of the inputs, and in order to move the fringes by changing its phase, in order to acquire data, and it's like that we can process the images and infer some astrophysical observables. Here I put a picture of the bench in the lab here in Paris. So you have at the top the injection of the source, of the light source, that goes onto the deformable mirror. Then it's reflected into the microlens array that is too small to be seen here, that focus light into optical fibers. All the blue wires are these optical fibers. Then it goes to the optical delay lines here on the left. After that, it's plugged to the photonic chip I talked about earlier. So you have the 5 fibers at the input on the left of the chip, and you have more. So it depends on the chip type, but you can have 10 or 20 outputs here on the right. This chip is plugged here on all this mess of fibers here to go on the spectrograph. So you have so essentially it goes into a V-groove. It's just the fibers put side by side, and the light just exits the fibers and goes onto the spectrograph here, and you have the camera at the end. So I don't know if you are familiar with pictures of optical bench, but it's quite a simple bench in this picture. Okay, so the scientific targets we are interested in are the young planets that are still accreting matter. So they are still being formed, and by accreting matter, they emit strong emission in H alpha. So they are very bright in H alpha, making it more easy to see with our instrument. So here are 2 pictures of 2 images of PDS of the system PDS 70 in H alpha, and you can even see on the right a disk structure. And yeah, we would the instrument works in visible, especially to be able to see these specific protoplanets. Because here on the tables, for instance, you can see that for this system in K-band, you have more difficult contrast ratio to achieve here on the order of thousands compared to on the order of tens, 100 in H alpha. So here are simulations about such a system. On the left, you have the H alpha emission of such a protoplanet that is accreting matter. And you can see that depending on some different accretion rates, you have a flux that is that could be detected by the instrument, because this flux here corresponds to these degrees in phase. The phase is what we measure in those fringes I showed you earlier, and 1 degree is fairly in the range of the capabilities of our instrument. So it could be very interesting to study these systems, because with the flux and the phase, you could infer the accretion rate of the protoplanet. And on the right, you have such a spectrum of such a system with the phase that could be detected with some baseline. So the baseline are just the length between the subtuples I showed you earlier. So it's really in the range of what we hope we could do. So in the lab, I simulated a binary source to show that we are capable of detecting such a system. So I injected a source with a large bandwidth to make the continuum, which corresponds to the central star. So here in dashed line, and I injected also a companion, what would be a companion with a laser at 635 nanometers with a flux ratio of 2. So you have the spectrum here of such a system. And this is what I could obtain with the instrument. So this is the phase signal we measure. Here in all the curves in colors correspond to all the baselines, so all the pairs of subtuples. And in dashed black line, you have the theoretical phase that we expect to measure. So it's pretty fair agreement. And as you can see here, you have 4 baseline on which you have no signal in the phase, and it is also expected because it corresponds to these 4 baselines. So here represented in the deformable mirror that are orthogonal to the binary system. When the baselines are orthogonal to the binary system, it couldn't see any phase, and the other baselines are like that, more with a component in the direction of the binary. So here I put a picture of the first instrument integrated at the Subaru telescope in Hawaii. So we started integration last September 2021, and you can see so on the right the camera. You have blue lines, which is the first V2, because the instrument I'm working on is the upgrade of the first V1 that already existed. That already exists at the Subaru telescope, and in red you have the path of the first V1 instrument. So we have side by side the two versions of the instrument imaged on the same camera, and on the left you have you can see the photonic chip that we integrated. Since last September, we had some observation nights. I could take a lot of data on some targets. So for now, it's mostly stars and binary stars because the flux ratio is more friendly, I would say. And I will have 2 more nights in March 23rd and 4th of April. And yeah, this is very preliminary results because yeah, it was difficult to obtain some good results from all this data. It's instrumentation, so we learn at each observation night we learn something new. But for now, on a single star, we have these phase measurements on that have a magnitude less than 0.5 radians. So yeah, the target would be to get less than 0.1 radians. So yeah, it's in pretty good path. And to conclude, so first has been fully characterized. If you're interested in that, I wrote a proceeding for a conference in 2020. And it's being integrated at the Subaru telescope. We acquire a lot of astrophysical data during several observation nights. There are a lot of work to do, still to do in the future. We are currently upgrading the spectrograph to gain in spectral resolution. We just changed last week the camera and the deformable mirror. And yeah, a student, Manon Lallemand, just started her PhD a few months ago to work on the project after me. And she will work on 3D printing of microlenses directly on the optical fibers. So yeah, there are very exciting work still to do. And I let you with some pictures of me when I went to Hawaii to observation nights. On the left, you can see the Subaru telescope, and on the right, picture of it outside near some other telescope and very near the place where the TMT would be built, as Ramya talked about before me. And thank you for your attention.
Excellent. Thank you so much, Kevin, for this interesting talk. So I now open the questions. I would like to remind people that are following this talk at YouTube, you can just post your question into the YouTube channel and I will read it for you. And participants here, you can raise your hand and ask the question by yourself, or even post it to the chat if you do not feel comfortable to do so. So right now, I don't see any raised hands, but I actually have a question by myself. So I've seen lots of impressive images of you ensembling the instrument in the lab on the optical bench, but now I also understand that it's already at the telescope. So how did this happen so quickly?
Yes, actually, when I started my PhD now 2.5 years ago, the bench was already built. So when I started my PhD, I mostly characterized the photonic chip that arrived at that time. So yeah, I just had to integrate the chip and to characterize it. I also work a lot on the development of the software control, the control software of the instrument. And yeah, for 2 years, the bench already existed, but yeah, I mostly characterized it and improve it in order to integrate it at the Subaru telescope. And the integration was only 6 months ago. So, yeah.
But it still seems that it's quite customizable, right? Because you were describing that you are upgrading the instrument, so it looks like it has a very smart construction in this way.
Yeah, we have some components that are replicated in Hawaii and here also. So that will be like that for the future, in the future, such that we can maybe test new stuff here in the lab in Paris and then send it to Hawaii. Yeah.
Nice, thank you. I can see that Louise has a raised hand.
Well, yeah, thank you. Thank you very much for a really interesting talk and yeah, really nice project. I was really happy to see the slides on PDS 70. And I was thinking about when focusing on this H alpha emission to say something about the accretion rate, if I remember correctly. How big of a problem would stellar activity or stellar variability be for this experiment? So is it a problem that the star most likely will be quite violent when it comes to changing H alpha emission?
I don't think so, because as long as we have a continuum of light coming from the star and a peak in the emission from another component, so the planet, we would still measure the phase.
Mm-hmm. Yeah. Okay. Thanks.
Very good. I don't see any questions raised in the YouTube. And there are also no more questions raised here. So I would like to thank Kevin again for your talk. You can stop sharing screen now. And I will hand over to Paola for concluding remarks.
Yes, thank you, Teresa. And so I would like to congratulate with Ramya and Kent about their talks. It was very interesting. I hope I really congratulate you for achieving first to present your work here. And I wish all the best for your future career. So for the audience, thank you a lot for attending these talks. And we have another slot next Tuesday. Hope to see many of you attending. Anyway, for those who missed the live event, can always catch up in YouTube. This video has been recorded and will be available there in the YouTube channel. So bye. Have a nice afternoon, nice days, and nice evening. Bye.